Hello and welcome. Today, we're going to pull back the skin, metaphorically, of course, to look at one of the most incredible, high stakes jobs happening inside you right now: hemostasis. It's the reason a tiny cut doesn't turn into a total disaster. So let's get right into how it all works. Think about it. You get a paper cut. It stings, it bleeds for a minute, and then you kind of forget about it, right? Later on, you look down and it's all sealed up. How does that happen? What's going on in there? Well, it's not magic, I can tell you that. It's actually a beautifully orchestrated, life-saving system. And that system, our hero for today, is called hemostasis. Now, its job is really a two-parter. First, obviously, is to stop you from bleeding out when you get hurt. But the second part is just as crucial. It has to do all that without, gumming up the works and causing dangerous clots anywhere else. It's this constant, delicate, high-wire balancing act. Okay, so to really get how this works, I want you to imagine hemostasis as your body's own microscopic, highly trained emergency crew. The second a blood vessel is breached, this crew just springs into action with a very specific three-step game plan. It happens like this. First, damage control. The blood vessel itself immediately clamps down and narrows to slow down the leak. It's like pinching a hole in a garden hose. Then, step 2, the first responders show up. These are tiny little things called platelets. They get the emergency signal, they swarm the site, and they form a temporary plug. But, and this is key, that plug is pretty unstable. So that brings us to step 3, the engineers arrive. They weave this incredible, strong mesh made of a protein called fibrin all over that plug, creating a solid, reliable seal. Right, so here's the big difference. The platelets, our first responders, are like an emergency crew, just slapping a tarp over a hole in the roof. It's super fast, but it's not going to hold forever. The coagulation cascade, that's our team of engineers. They're the ones who show up to build a proper, reinforced structure, that fibrin mesh that's actually going to last. And this cascade, it's this beautiful chain reaction of proteins activating other proteins, all leading to that final stable clot. It's amazing stuff. So that's the ideal scenario. But what happens when that perfectly balanced system gets thrown out of whack? Let's look at what happens when the emergency crew is, say, understaffed or maybe missing a few key members. This is the story of bleeding disorders. And what's wild is that this is not a new problem. This quote right here is from the Babylonian Talmud, written nearly 2,000 years ago. It's one of the earliest written descriptions of an inherited bleeding disorder we've ever found. It's ancient, practical medical advice, right? If there's a genetic bleeding issue in your family, maybe skip that procedure. It just shows that humanity has been aware of this and grappling with it for millennia. And maybe the most famous historical example of this is hemophilia, which was often called the royal disease. It all started with Queen Victoria, who was a carrier. Through the marriages of her children, that faulty gene spread like wildfire into the royal houses of Spain, Germany, and most tragically, Russia. The young heir, Alexei, suffered terribly from it. It's a perfect illustration of how a single genetic quirk can literally alter the course of history. Now, there are a few main types of these disorders. Von Willebrand disease is actually the most common. Then you have the more famous ones, hemophilia A and hemophilia B. They're both caused by a missing factor, which is just one of the crucial protein links in that coagulation cascade we talked about. If you're missing one of those links, you just can't build that final fibrin seal properly. And a little fun fact, hemophilia B is also known as Christmas factor, not because of the holiday, but named after the very first patient identified with it, a boy named Stephen Christmas. Okay, so that's what happens when the clotting system is too weak. But now let's flip the coin. What happens when the crew goes rogue? When it starts building clots where they absolutely shouldn't be? Well, that's called thrombosis. And let me tell you, this is a massive, massive problem. This number you're looking at, 600,000, that is the number of people who die every single year from venous thromboembolism, or VTE, in just the US and the UK combined. Over 500,000 people. It's actually the #1 killer in the Western world. And to really put that number into perspective, just look at this. VTE, an unwanted blood clot, is responsible for more deaths every single year than breast cancer, car accidents, and AIDS, all combined. It's staggering. And what's even crazier is that it's the leading cause of preventable hospital death. So why does this happen? Well, way back in 1856, a doctor named Rudolf Virchow figured out the 3 main culprits, what we now call Virchow's triad. First, something's off with your blood flow, like when your blood gets stagnant from being stuck on a long flight or after surgery. Second, something's wrong with the blood itself, maybe a genetic mutation that makes you more prone to clotting. And third, there's damage to the blood vessel wall itself, like from those atherosclerotic plaques we're always hearing about. So we have this unbelievably delicate balance, right? Swinging between fatal bleeding on one side and deadly clotting on the other. How does modern medicine step in to figure out what's wrong and, restore order? It's time to call in the medics. To figure out what's going on, one of the first things doctors will do is run a couple of basic clotting tests. The two big ones are the PT and the APTT. What they do is pretty simple. They measure how long it takes for a sample of your blood to clot in a test tube. Each test looks at a different pathway, a different set of those clotting factor proteins. So if one of these times is way off from the normal range, it gives doctors a massive clue as to which part of the emergency crew isn't doing its job. And our ability to actually treat these problems has come so far. Back in the 80s, treatment meant giving patients clotting factors that came from donated blood plasma. But this led to an absolute tragedy, a massive HIV crisis, because the virus was being transmitted through contaminated blood. That horror spurred the development of much safer lab-grown recombinant factors. And just recently, in 2022, science took another huge leap with the approval of the first gene therapies for hemophilia B, which offer the incredible promise of a long-term, maybe even permanent fix. So as we start to wrap this up, let's bring it all back to that central idea. This whole entire process, from the tiniest paper cut to the most complex genetic disease, it is all about maintaining a perfect, delicate equilibrium. At the end of the day, hemostasis is your body's silent guardian. It's an invisible, life-saving balancing act that's being performed constantly, 24/7, without you ever even having to think about it. It's this intricate dance between the forces that want to make a clot and the forces that want to prevent one, all to make sure your blood stays liquid and flowing but is ready in a split second to become a solid, life-saving seal. It's honestly incredible when you stop to think about it. And it kind of leaves you with one final thought. Hemostasis is just one of who knows how many invisible systems working around the clock to keep you alive. What other amazing biological processes are protecting you right now as you're sitting there? Thanks for watching.